We're going to take some time now to review over what we know about exponents, and then preview and also review a little bit about what we've done with radicals and try to tie them together. So first of all, let's do these rules for exponents. First of all, the product of powers, that's going to be when you have a to the m times a to the n. That's going to equal a to the m plus n, because you've got m factors of a, n factors of a. You bring it together, you have m plus n factors of a, because exponents refer to multiplication. You're going to add those exponents for this one. Quotient of powers is when you divide, so a to the m over a to the n. Division, you're going to take away the factors of a in the denominator, so that means you're going to subtract the exponents. M minus n, because you're taking away factors as the quotient implies. Power of a power is when you have a to the m to the n powers, so you're going to have a to the m written out n times. You're adding those m's together with the first rule. That also is simpler by just multiplying the m times the n. So bring the n in, multiply it by the m. Now, power of a product, this is where you have to remember that if you're going to have two numbers on the inside here to an exponent, that exponent has to come into each of the terms on the inside. It's got to come into the a, and it's also got to come into the n. So bring the nth power into the a and the n, each of the individual factors on the inside. Negative exponent we've already done, but we want to review this. If you've got it to a to the opposite of m power, you want to recognize that that means you're going to reciprocate it. Make the m a positive, but put it in the denominator. It becomes 1 over a to the m. And this is our new one. This is going to be tying it to our radicals. If you've got an exponent that is a fraction, a to the m over n power. So the fraction isn't outside, that fraction is in the exponent. The denominator of the exponent becomes the index. It becomes nth root of a to the m power. So the numerator becomes the exponent, the denominator becomes the index in the problem. That's new. That's going to be what we build upon in the next few lessons. Now let's do some examples here. Let's try this example where we're going to go ahead and simplify this. The first part doesn't need the parentheses because there's no exponent on the outside of it. But this one, I need to bring that fifth power into each factor. Don't forget the constant. This is where people forget that that fifth power also goes, this is implied to be 2 to the first. 5 times 1 becomes 2 to the fifth. X to the 5 times 5 power, and then y to the 2 times 5 power. So it comes into each of them, and then when there's already an exponent, you multiply by it. So this one I'm going to leave alone for just a moment. 2 to the 5th is equal to 32, x to the 25th power, y to the 10th power. Now when I take this, I'm going to rearrange. I'm going to do 7 times 32 in the front, times x, there's an x to the 4th, an x to the 25th. I'm going to add those exponents. I've got a y to the 3rd, y to the 10th. I'm going to add those exponents because they're the same base. And now I get 7 times 32 gives me 224. X to the 29th power, y to the 13th power is my final answer. So that's how you simplify these two as you bring them together. This one again, I'm going to bring that 2 into each of these terms, 5 squared. This is x to the first. When I multiply the 2 times it, it also gets an x squared. And then y to the 3 times 2, I'm going to go ahead and multiply those two, and I get the 6th power. Remember, it's multiplication when you bring it in. And then times 4, x to the 8th, y to the 10th. X squared is equal to 25, so I'm going to have 25 times 4 in the front. Multiply the numbers, bring those together. X to the 2 plus 8 power here. y to the 6 plus 10 power here when I have the same base. So 25 times 4 is 100, x to the 10th, y to the 16th, for a simplified form of that answer. Now let's go back and we're going to do a little review of radicals and how you simplify them, and then we're also going to preview a little bit of some of the what we'll do with different indexes than square roots. So first of all, a reminder that the square root of 144, what that's asking is, it's saying, what do you square to get 144? So that one we might know already to be just 12. Okay, so that one comes out nice and complete. It's a nice, neat integer. Same thing here. We're asking, what do you cube to be 125? Well, 5 cubed is equal to 125. So you can make that equal to a 5. Now, if you wanted to do that on your calculator, what you could do, just as a reminder from what we learned up there, you could take the 125 and make it the 1/3 power. It's 125 to the first power. You put the 3 as the denominator. You could do this on your calculator and you would get that 5 as an answer. Now let's go ahead and do this next one. As a reminder, review a little bit. When we get the square root of a negative, that means you've got to take the I out. You've got to separate this into square root of -1 times square root of 169 plus the square root of 49. Now let's do the square roots. This is equal to an I. This is equal to 13. 13 squared is equal to 169. And the square root of 49 is equal to 7. Now we typically don't leave it in that notation. When we do a complex number, we put the real part first. So you can have a 7 plus, and then you put the imaginary part second. So we put 7 plus 13i when you're writing that out. All right, let's do this last one. Let's review over what we know about function notation and apply it to these functions. And we use these two functions, f of x and g of x, and find these two here and then add them together. So first of all, let's do f of 2. F of 2 means 2 becomes the input in this function. So we have the square root of 3 times 2 minus 4, which is the square root of 6 minus 4. And that's going to be equal to the square root of 2. All right, so for the next part then, what we're going to do is we're going to do g of 12. G of 12 is I go to this function and I put 12 in for it. So I'm going to put 10 times 12 as the input. That gives me the square root of 120. Now this one, what I want to do is I want to go ahead and simplify it. So I'll do that first before I put it in the rest of the problem. What perfect square goes into 120? Well, if you think about it, you got to go through some of your perfect squares. 4 goes into it. So I'm going to make this the square root of 4 times the square root of 30. The square root of 4 is equal to 2. That becomes the coefficient of the square root of 30. So now when I do f of 2 plus g of 12, I'm going to write out what I got for f of 2 is square root of 2. I got this 2 square roots of 30 for my g of 12. And so when I add those together, they're not like terms, and we'll talk more about radical-like terms later, but these two radicals are not the same, so I cannot add them together. So that is the final answer. You can't add radicals together unless the radicand are like. So these are not similar terms. So when they're not similar terms, you can't add them together. So what we've done is we've reviewed over some of the exponent rules that we've learned before, and then we've also applied some of that to our radicals, talked about what we knew before about radicals, and then started talking about newer ideas about simplifying radicals.